Thank you for coming along during this half-term sort of session, May 2023, and we're lucky enough to have Dr. Hannah Wakeford here talking about exoplanets. Okay, well, actually, specifically, what's around them, their atmospheres. So we're going to have an exciting dive into an exoplanet atmosphere. From what I know, and I hope to be corrected, but most of them will kill you if you try to dive through them. But we shall find out, hopefully, as we go on. Right, did I actually click? Yeah, I thought I did. Let's try again. Yeah, okay, that works better. Okay, darkness begone month. Yes, we have no darkness, it's just twilight now. But as we proved on Saturday night, you can still do lots with summer twilight. You just change your subjects, really. Galaxies aren't so exciting, but you've got all the double stars, you've got globs stand out enough, you've got Venus is looking amazing. Mars is still there, but perhaps not as exciting as it was 6 months ago, or actually a bit longer than that, 8 months ago. But it's still worth a look. And we did solar observing this weekend as well for public as well, which you could, everyone's sort of welcome to come along to and get to see what's exploding on the sun. And this one on Saturday was particularly good because we're all looking at it and going, it's a bit dull today. Right. Now, for someone who hasn't seen the sun before, that's sort of like, all right, it's the sun, wow, like that's amazing. But it wasn't doing any explodey things. And then Prim's not here tonight, but Prim said, oh, what's that? We're just seeing a coronal mass ejection just occurring off the side of the sun. And we watched it over the next 15 to 20 minutes exploding completely off the sun, and the sort of the remnants of it falling back as coronal rain, and just going, that's kind of exciting. So it wasn't as good as, say, some of the static prominences we've had before in terms of the whole session, but that 15 minutes to 30 minutes was really quite spectacular, watching something sort of the size of a continent moving off the side, even bigger, coming off the side of the sun and heading out. And it's on the side that rotates towards us as well, so that's going to swing round. But that was more than a couple of days ago, and it obviously missed us this time. Right, great. So if you see any of these lovely people, they are your coordination team. Again, stop them, say hello. I'm sure they'd like a chat. Current membership is 104, so we're sort of holding steady just above the 100, so that's kind of nice. And I talked about this, so yeah, we're the summer outreach, so we're doing loads of solar. What we did last year is we begged, borrowed and stole and got people to bring their own telescopes. Now we've actually got the society owns, what is it, 3 solar telescopes now. So we can do H alpha on the PST, we can do H alpha using a Daystar quark, but on a longer telescope, so you get better magnification. It's got a larger aperture, so better resolution. So we can zoom in on prominences. So we've got context in the PST with the whole sun, and then we've got zoom in, and then we've got this one here is a Herschel wedge, so we can do white light on there as well. So it gives us a range, and Roger was good enough to bring along his Williams optics with his Daystar quark as well. So it gave us a nice range, and we could send people on a sort of, have a look in that one, get context, have a look in that one, and have a look, and then they could actually go across all 4 of them, which was really quite nice and sort of good for the engagement side, rather than just a quick visit. Oh, I've seen the sun. Tick, tick. But yeah, so gosh, so we've done 2 weekends of it. So we've probably done about 150 plus members of the public who come look through the telescopes. So we did Royal Victoria Park, and then we did Sydney Gardens just this weekend gone. So we're going to be doing more. So watch this space. If you'd like to get involved, if you'd like to know how to use the telescopes, we can do a quick training session and do's and don'ts, and then you can sort of buddy up with someone over a weekend. And then if you feel confident, and I see that you're sort of, you've got enough confidence and you know what you're doing, then effectively you could be running one of these and telling the public a little bit about the sun. That's all people want to know, is a little bit. So you don't need to be experts in anything you do. You just need to know a bit more than the person that's looking through the telescope, so you can sort of engage their interest and sort of take that to the next level. And we've gone a bit overboard on the carry out now. So before we just gave them a sticker, which was lovely. I've seen the sun, or my spotty sun, and so everyone was walking around town with their spotty stickers. But now we've got an A3 handout, which has got interesting facts about the sun. It's got how to observe the sun safely. Nice big warnings on it. QR code linking back to us. But on the flip side is an A3 poster to go on your bedroom wall or on your refrigerator, which all the sort of parts of the atmosphere and the surface of the sun. So it's sort of like a heliopedia. It's stolen but credited to NASA and their promotion teams. So it's a bit of work, but we've got 2,000 copies of this, and we've got rid of about 300 already. I'm not sure how we got rid of so many. Handed out so many when we actually only had about 150 viewers. I think people maybe took them, and it was things like parents and things taking them for schools, and one for you and one for the school, I think, was going on. But it's great because we got 2,000 for that reason, to spread the word and get people thinking about astronomy. So that's actually been a very popular, the poster size thing has become quite popular. So we'll look to see and get a few more of those out. The loan box, we've had rave reviews. You may have read the newsletter. The school, St Patrick's in Corsham, absolutely loved it. And we managed to get it back from them just this last week. So in there, we've got the Tellurium, which is the model of the moon, the Earth and the sun. So you can do all that lessons. We've got making spectrometers, not spectrometers. So little card things you can split sunlight up to have a look through. We've got making planispheres in there. We've got a gravity well. We've got so you can simulate how the planets go around the sun. And then below that, there's a level of binoculars. There's binoculars for the entire class. And then below that still is a fully working GO2 telescope. So they get this flight case. They kind of think that maybe they're sort of roadies to the latest rock band or whatever, but it's full of astro gear with instructions on how and all the things to use. And then it's got that apt warning on the front, may contain black holes. So yeah, the feedback we've got is really good. We've got no bookings over the summer, but that was sort of to be, or this summer term coming, it's kind of expected because schools are doing exams plus sports day and all those kind of things. Space is actually typically October, November, or January is when schools do it. So we've got a booking for the first time it can be booked out. We've got a booking for it already. So hopefully onwards and upwards on that. I'd like to thank Camilla, who put it all together. She, up until last week, was part of the coordination team, but she's just stepping down. She's still going to support all our outreach activities, STEM, sort of be our STEM expert. But she, you might not know, but she runs sort of robotic competitions for sort of a group of schools called, I think it's Wishford, the Wishford schools. And it's basically taking her to like all these different schools running competitions where the kids compete making these robots to do tasks, and then they go into sort of regional finals and national finals. And last year she was off, I think it was to, was it Dallas or Houston? Okay, it was Texas anyway. So her school actually won the UK, and so she took them over to the States to compete against the, actually it was a world stage, but most of them were Americans. So that's keeping her really busy, and she does loads of singing with her group as well. And I think they're going to Glastonbury, so perhaps she needs a bit more practice. But thank you very much, Camilla. I'm not sure if you're there or listening, but very much appreciate all the hard work. And thank you for your commitment to keep working on the loan box and the materials and the things around that. And the other thing that's happening is that whenever we do stargazing around here, or whenever you come and visit the museum, there's not much actually about the night sky here. There's a few books, but most of it's about the history of William and Caroline living in this house. So we're writing their guide for actual seasonal looking at the night sky. So that will be available at the front desk for free and at all the events. So they'll have one for summer, autumn, winter and spring, just rotate it around. And it just gives a bit of an intro to sort of astronomy and sort of like that next step to sort of get people interested, get people engaged. So little articles about why there are no green stars, tiny little article just to explain why you don't see any green stars. The comets that Caroline found. So stuff like that against a good thing to look at, like the summer triangle. So just a balance, really short little handout, but we're glad to, when I say we're glad to, there's a lot of work doing these things. but we should get the first one printed, so it'll actually be downstairs in 2 or 3 weeks, and then we'll go on to the autumn one, which I've just finished writing. Other things that are happening. Anyone want a telescope? So this 19th century Sir Howard Grubb of Dublin telescope. So it's 123 years old, and it was removed from a university legally back in 1990, and it's been in someone's garage for 33 years because it's a project they were going to do. Unfortunately, they've passed away now, and it's their son that has donated this to Bath astronomers. The optics look great. In fact, it looks like a fully working telescope with a bit of rust. So it's about a matter of sort of a bit of a cleanup and finding the right location and the right home for it. So it should be a much easier project than the one we did at Monkton Combe, where the telescope was literally falling apart and we actually had to repair it. Most of the bits are there. In fact, as usual, when we have any of these projects where things are dismantled, it's the bolts that are holding everything together. Someone puts in a nice bag. Okay, so you find all the big bits, but the nice bag full of all the bolts, that never comes with the donation. That's somewhere else in someone's house somewhere. I thought this was the same case. I've got an email today from the gentleman that's donated it saying, I just found this bag of bolts. And it's exactly the bolts that we need to put it together. So hurrah, because they're all non-metric, they're all interesting fits. So it's great to have those rather than having to source them. So Mike, if you're out there, I know you've already offered to help us out with that one. I will be annoying you soon. And then we'll have a good look at it and see what the best way to sympathetically restore it. And then we'll try and find a home for it. What else is happening? This is Toppings. You might know York Street. We're going to basically attack this street on August the 13th, Sunday, August the 13th. So if you're around and you can help, either actively sort of doing a bit of outreach or just coming along, we'll have gazebos here, we'll have solar telescopes looking up here. Toppings are doing a display of all their space books, and we're just trying to see if we can get a few authors to come in and do some talks around within the Toppings building, sort of like spacebook authors as well. So we'll see if we can get that organized. Well, we're going to be here. The only bit that we're just trying to get sort of a handle on is the authors talks supported by Toppings Bookshop here as well. So it should be busy, should be fun. This is normally absolutely bustling with people. So we're going to be right in their way. So it's going to be either wonderfully active or people are going to go, brr, but we'll find out. It's the bid team, the sort of Bath development organisation that's sponsored by the council that sort of asked us because we ran a really successful pop-up shop for them last year. And so this is their offices here. So we're running it actually out of their offices. Okay, so that should be quite nice and exciting. And why on earth have I got a plan that's been submitted to the planning office here? This is Prior Park College. So the college continues all the way down here. You probably can't read why, but the area of interest is here. They're putting up a new little 2.5 meter dome, and we are the consultants on this project. Now, normally you'd think just put a bit of concrete down. It's a shed, and they've had to go through full planning permission. And this is the planning submission on how they're going to obscure this white building from the rest of Bath because it's on the skyline. So this was the planning for the planting they're going to be doing, the new paths, and then sort of another area of planting here to obscure the white dome from the rest from Bath. Okay, so I just put mine up with a bit of concrete. They've gone through a bit more fun. But one of the reasons why we're consultants on this, what's in it for us is we're going to get access to it. So we'll be able to run sessions for Prior Park and with Prior Park. In fact, it's the same relationship or very similar relationship to the one we've got with Monkton Combe School and the Victorian Telescope. So it gives us another option for places to be and things to do. So we're building relationships, loving it. They haven't got planning permission yet. It was supposed to be given last week. So maybe these shrubs aren't big enough. Maybe they're not green enough. I don't know. Or it could be that we do know the planning office has got a bit of a backlog at the moment. So whatever. Gosh, I've spoken too long, haven't I? Yep. over my 15 minutes. So just to go through what have we got coming up. We've got Mary McIntyre next week, next month, and then we'll kick off. Everyone can have some time off in July and August. You can do whatever you like. We're still going to be doing loads of activities, but no formal talks. Dr. Becky Smethurst is coming to, is that door? Dr. Becky Smethurst is coming to talk to us in September. So Dr. Becky, she's got, gosh, 500,000 followers on YouTube. She does sort of weekly sort of podcasts and things. She's also part of the Supermassive podcast with the Royal Astronomical Society. Does loads of stuff. Dame Jocelyn Bell-Burnell, bless her heart, says, I think she does a bit too much of the podcasting. I think Dame Jocelyn would prefer people to do a bit more solid science and things. But no, science communication is a very important aspect as well. So I'd probably argue that actually if you can get the balance, it's great. Steve Warbis, he's a keen amateur astronomer. There's a couple of subjects he could talk to us about, so we're just going to decide which is probably going to be best, because one of them is astrophotography, but it's looking at whether we're going to have another astrophotography a little bit later on, to whether we use Steve for astrophotography or not. Richard Hook used to work for European Southern Observatories, and so he'll be talking about the big observatories. He'll be talking about sort of the ELT, so the VLT, the ELT to be, what Vera Rubin's going to do. Now, hopefully Vera Rubin's going to do first light within the next year or so. So fingers crossed on that. So it's great. And it just goes on. We're still booking out. So we've still got a couple more slots, which hopefully will get confirmed in the next few weeks for April and May. But then we'll be done for the whole of next year. Okay. So an exciting lineup, I hope. And I hope you enjoy it. Right. We have got Mary next week. Next week, keep saying next month. And she'll be talking about a history of women in astronomy. She's actually given us the first part 1, which has taken us up to Caroline Herschel. She's going to be going beyond that now, sort of a modern history of women in astronomy, pulling out some names that you've never heard of, perhaps you should have heard of. So that'll be fun and exciting. But quickly, let's move on to Hannah, because I've talked way too long. And she's been so lovely because there's free stickers here. Always. Right, for everyone here. So if you're online, you don't get a sticker. Okay, so there's always a good reason for coming to these sessions. You get free stickers. You can keep them. You can, okay, can I? Okay, thanks very much. So Hannah, wow, you're so young, and yet your career, when I read your bio, sort of, you've done so much. So was it University of Wales, was where you got your first degree? Yeah. And then was it Exeter? You got your PhD, but you went to, was it the Institute of Svalbard? University Centre in Svalbard, yeah. Wow, and that sounds cold. It is cold. Yeah, okay. It's wonderful. It's in the Arctic, so it's as cold as the Arctic. And then you've gone on to do various placements all in the States. Mm-hmm. So Goddard, you spent, was it 2 or 3 years? 2 years at Goddard, 2 years. Yeah. And then back at Exeter, I think, for a while, just for a short period. To get a visa. Because you want to get back as quickly as possible. It was a visa secondment from the US government, who didn't want me for a bit, but yeah, I was back here for a few months, and then. Okay, and then you were off to, was it the Space Telescope? Space Telescope Science Institute, yeah. Yeah, so James Webb, Hubble, sort of the home, the centre of it all. And now you're lecturing in Bristol in astrophysics. Excellent. So what I'll do is I'll just give us a couple of minutes while I just flip over presentations. Then wonderful. Hannah will take over. I'll take the clicker. I'm not going to press the big button at the bottom, which cancels everything. Accidentally hit it at some point. It's okay. I can recover it. There we go. I got it. Good. Okay. If you could just wave at me when you want me to stop, and then that will.
So thank you for coming along for this. I'm gonna talk to you, as Simon said, about exoplanets and their atmospheres, but I'm going to take you through it bit by bit. So if you don't know too much, hopefully we're just going to build up that knowledge and take a logical walk through some of the work that I do with my teams across the world, and how we're using these space-based telescopes to investigate these alien worlds. So I think the first question is always important. What is an exoplanet? So an exoplanet is a planet that orbits a star other than the sun. So these are all planets that are outside of our solar system, orbiting the stars that we see in the night sky. Many of the stars we don't see in the night sky. So we only see a very, very small fraction of the stars, the really brightest or the closest stars to us. We're often looking about 700 to 1,000 light years away, even more sometimes. So we are looking at quite distant stars, but I'll show you a little bit about where those stars are as well. But the one thing that I really like to start with is a bit of history. And actually, this is kind of a perfect place for a bit of history in a museum. It's the best place to be. But exoplanets are not new.
Just bear with me.
You're not sharing your screen. It's okay.
My brain is only just engaged.
Didn't miss anything, everybody. Slide 3. It's the first picture that we've got. So exoplanets really were thought of back in ancient Greek philosophy. About 450 BC is the first written mention of planets being thought of as existing outside of our own. And this comes as a foundation of Epicurean philosophy, where they believed that absolutely everything in the universe is infinite, and therefore the statement followed that there must be an infinite number of planets, both like and unlike our own planet. So it wasn't even there must be an infinite number of Earths out there, but like and unlike, meaning they were thinking about the fact that this isn't the only manifestation of what a planet is. So the thought about looking for and understanding planets other than our own has been around for a really long time. But it wasn't actually until the scientific renaissance in the 1600s that the first postulation of how can we measure these planets, how can we measure planets that are outside of our solar system around other stars, really came about. And this was work by Christian Huygens, where he was using some of the first telescopes to look at Jupiter and its moons. And what he saw was that the moons cast shadows on Jupiter. And he postulated that if we were to look at other stars, we could see the shadows of planets passing in front of those stars. So very similar to what they were measuring at the time with Venus transits. Could we look at the transit, the passing, the shadow of another planet on a star? Now, there's a big problem with that. One is that in the 1600s, they had no idea how far away the stars were. So did not have a concept of how small that measurement would be. How little light would be blocked by those planets if we're looking at a distant star. So it actually took about 200 years before the first claim of an exoplanet, a planet outside of our solar system orbiting another star, was made. This was done by W.S. Jacob at the Madras Observatory in India. He worked for the Southeast Company. He looked at a star called 70 Ophiuchi, and he was monitoring this star over time. And what he saw was that the star moved. He measured how that star moved, and he said, this is the first scientific publication that was submitted to the Royal Society, stating that there is this exoplanet, this planet orbiting this star. He said that because the star is moving, something is pulling on it, and that something must be a planet. Now, unfortunately, again, we still didn't have a great idea of all of the stars in our local neighborhood, how far away they were, and therefore what you were really measuring. And if you don't already recognize the star, 70 Ophiuchi is in fact a binary star system. So what he was measuring was the pull of another much, much smaller and essentially invisible star at that time on the main star 70 Ophiuchi. So asterisk, first claim of an exoplanet, first false claim of an exoplanet. So we actually have to travel another 200 years into the future from this before we get the first detection of an exoplanet orbiting a sun-like star in 1995. And since then, what we've been learning is that, in fact, nearly all of the stars that we see have planets around them. So I want you to imagine throughout this talk, because it's one of the hardest things to think about. We're not great with really big numbers. It's just not possible. But one way that I really like to think about this, there are more planets than there are stars. There are more stars than grains of sand on the Earth. Can you fathom that number? There is a huge number of worlds out there. So I think we go right back to Greek philosophy, saying that there are infinite number of worlds, both like and unlike our own. And one of the things that we're trying to do right now is trying to understand what those worlds are like and what they're like compared to our own, and how we can use that to learn more about our own planet. So if we look at these different planets, we can actually put on a map of our sky. So this is a Gaia map of our sky. So you can see the Milky Way threading through here. Every single dot on here represents a star where we have measured and confirmed the presence of an exoplanet. There are over 5,000 on here, but there are some distinct things that you might be able to spot. One I've highlighted for you up in the top here, this really dense cluster that you can see. That is the footprint of the Kepler Space Telescope. The Kepler Space Telescope was launched in 2009. Its job was to sit and stare at a single point on the sky for 3 years solid. It sat and it stared at that point just by Lyra and Cygnus constellations in the southern hemisphere. Well, kind of on the edge. And it was looking for these planets passing in front of their star. Those transits, those shadows that Christian Huygens postulated to exist back in the 1600s, it was sitting there and it was staring at 150,000 stars, trying to see those shadows passing in front of them. You can see the Kepler footprint actually repeat itself across the ecliptic as well. These little clusters is what was done with the mission following that 3 years. It then went on to a survey mission where it was looking at different patches along the sky. And there was a number of issues with the telescope. Some things broke, the gyroscopes being one of those things that broke. That's the thing that allows it to point accurately and maintain its position. Once they lost control of those gyroscopes, the pointing was not controlled. So the reason we've got those along the ecliptic is because it was literally using the solar wind pressure to point the telescope. And that is lined along the ecliptic, which meant that we could point it along those for a couple of months at a time. So each of these dots here represents a star with an exoplanet around it. And I say an, but some of these have multiple planets around them. We are not the only 8-planet system. In fact, we have found a planetary system with 9 large planets around it. So those numbers are growing. We're starting to try and understand what that means and how that puts our solar system in context.
Can you explain the color coding?
Yes, of course. So the colors on here represent the temperature of the star that they are around. The bluer the dot, the hotter and bigger the star. The redder the dot, the smaller and colder the star. One of the other things that's important is this is our timeline of discovery. If you look down at the sun on the Orion spur, each dot represents the position relative to us for all of those 5,000 dots. So while we have discovered, I'm going to keep looping through this, while we have discovered these 5,000 planets, they are really all within our local solar neighborhood. And that's just quite simply due to the fact that we're measuring these stars. It is easier for us to measure something bright and nearby. So there is a lot of observation bias in what we're able to measure and therefore draw our understanding from. But the beauty of looking so close to our sun is we can also understand our local neighborhood as well really nicely. And one of the really, really amazing things that we've discovered, this is one of the most important things we've discovered. What you're looking at here is a graph of the number of planets per star versus the size of those planets. So as we go along, we've got this big green line here that represents the Earth's radius. The blue lines are Uranus and Neptune, and the orange lines are Saturn and Jupiter. This histogram is showing you that, in fact, the most dominant size of planet that we have discovered is somewhere between Earth, the largest rocky planet in our solar system, and Neptune, the smallest gas giant in our solar system. Over 50% of the planets that have been discovered so far lie in that radius range. And yet our solar system does not contain a planet within that size range. So our solar system does not have a representative for what is the most common type of planet that has been discovered. And that leaves us with a whole host of questions that we are desperately trying to answer. What are these worlds like? But some of you might notice that, in fact, there's this dip in between. Not only is there a majority of worlds between Earth and Neptune, but there are two different kind of categories there. Now, you're all astronomers. You might have noticed we're really bad at naming things. Like really bad at naming things. Astronomy is what I call a say what you see kind of science. We describe things. So what might these planets have been named? We've got these planets here in this first category right by the Earth, that green line, that are bigger than the Earth. These are called super Earths. And this cluster of worlds that exist in a radius space just smaller than Neptune are called mini Neptunes. We're going to see some say what you sees as we go through all of this, and you'll notice that it's across all of astronomy. We just say what you see. Yeah.
Is there a correlation between the size of the sun and either the size or the quantity of planets found around it?
That is an excellent question, and I will be able to get to that a little bit later, but it's based on the fact that the smaller the star, the smaller the planet we can measure for those stars. The majority of stars that we have locally and in the universe are much, much smaller than the sun. So the probabilities are helpful there, but the smaller the star, the dimmer it is, so the harder it is to measure. So actually there's a whole host of different factors which play into that. But the important thing about this diagram is actually we're only looking here at stars like the sun. So while this is a good representation of the population of exoplanets, it still is only talking about a small fraction of the ones that have been discovered. So if we include in this diagram stars that are unlike the sun, so small cold stars, the histogram looks very similar, but is more dominated towards those small planets, because the smaller the star, the less material around it to be able to form giant planets like Jupiter. So I'm going to introduce you to my fruit basket of planets, because we're going to try and imagine what these worlds look like. And in a fruit basket, you always need a pea. Why not? We're going to represent the size of the Earth as a pea. And it's nice because it's going to be unique in our fruit basket as well, just like the Earth is. So on this scale, we're actually going to put in that our giant planets, our Uranus and Neptunes, are about the size of a nice plum. They're about 4 times the radius of the Earth. Our Jupiters and our Saturns are an orange, about 11 times the radius of the Earth. So on this scale, with our super Earths and our mini Neptunes, we get our blueberries for our super Earths and our grapes for our mini Neptunes, which is also quite helpful because these come in bunches, as do our super Earths and our mini Neptunes. So we can see that in our solar system, we've got this kind of representation of different worlds. But one of the things that we're finding when we're looking at these exoplanets is, in fact, they don't really look like our solar system at all. And we can see that really clearly when we do this kind of graph, where on the bottom, we've got the separation from the star in astronomical units. That's measurement from the Earth to the sun. And then up the side is the mass of that planet. So I put the representation of the sizes on there as well, and then the masses of those planets. And you can see our solar system planets in there. And what you'll notice from this is that most of these planets that we've discovered are much, much closer to their stars than our solar system planets are to the sun. In fact, a majority of these worlds, if we look up, are even closer than Mercury is, which goes well off the bottom of the scale here in terms of the mass. They're about 20 times closer to their stars than we are to the sun. That's 8 times closer than Mercury is to the sun. So these are incredibly close, short orbital period planets. And that is purely due to the observational bias we have. The closer the planet is to the star, the more times it orbits that star in the amount of time we can observe it. The more times that we can observe it, the more information we get from it. And we can confirm that it is, in fact, a planet orbiting that star. So it is much harder for us to measure things like the Earth, which would only pass in front of the star once per year, or Jupiter once every 12 years, or Uranus every 45 years. So there is an observational bias in the measurements and the known confirmed exoplanets that we are able to investigate. However, there's some things in here that are not an observational bias. And one of those is this really important region right here, where there appears to be a complete absence of planets. This is called the Neptune Desert, as they are Neptune-Uranus sized, but there's not many of them. There is a desert of Neptune-sized worlds very close to their star. And what is thought to be happening there is, in fact, they're so close to their star, but they're not massive enough to hold on to their atmosphere. So the atmosphere has been blown away over time. So we're starting to understand and learn more about the environment these planets are in and what that might mean for the nature of their climates. Another thing that we can learn from the fact that these planets are so close to their star, I mean, they're orbiting in less than 10 days. Some of them are orbiting their stars in 24 hours. They're incredibly close to their stars. And because of this, they experience what is known as tidal locking. Very much like the moon, these planets are tidally locked to their stars such that there is a permanent day side and a permanent night side. We only see one face of the moon from the Earth because it is tidally locked to the Earth. What tidally locking means is that its orbital period matches its rotational period. So if we look at our Jupiter going around its star, it's rotating at the same rate that it is orbiting that star. And therefore, one face of that planet is always facing the star, and one face is always facing space. And this has huge implications for what's happening in the atmosphere, the dynamics of that planet's atmosphere, where radiation is going on one side of the planet, driving winds and transport around that planet to a colder night side. Another thing that's really important, and we kind of saw a hint at that from the population of planets across the sky and the colors of those dots, is that these planets are orbiting different kinds of stars. And we've got these, again, say what you see, small, cool red stars. The small red stars are called red dwarf stars. through to solar-like stars, which are medium kind of warm yellow stars, to these big, hot, giant blue stars called blue giants. Now, the important thing about these different kinds of stars is the different size of the stars represents a different temperature. The different colors are the different temperatures of those stars. The smaller, redder stars are colder than these giant hot stars. The sun is about 6,000 Kelvin. These cool stars are in the 2,000s, 3,000s to 4,000 Kelvin. And these really giant hot stars are in excess of 10,000 Kelvin. The implication for the temperature of the star and that orbital period of our planet can be represented in the temperature of those worlds. So we can take an understanding of our solar system and we can apply that to these different types of stars. We're actually only looking here at stars smaller than the sun. So the top line up here is the sun with the solar system planets along it. As we go down to these small red stars, we're going to smaller and colder stars. And what we can do is we can take the Earth as it is now with the atmosphere that we live and breathe, and we can ask the question, if I moved the Earth relative to these different kinds of stars, where would it be orbiting around those stars to have the same temperature profile? And we then set these limits where water can exist as a liquid. So essentially we're between 100 degrees close to the star, 0 degrees far away from the star. Hot inside, cold outside. Where could the Earth and its atmosphere exist relative to these different sizes of stars? And you get what we call the habitable zone, the Goldilocks zone. I like to use the possible liquid water zone because, again, it's science. It's potential. There is potential for liquid water. It does not mean it exists in this region. There's potential for it to exist in this region simply due to the temperature that you would have for that planet. But what you can see is that the smaller the star that we get, the closer you have to be to that star for you to be that temperature. So when we're looking at these small stars, we are actually looking for planets on orbital periods of days around those stars to represent the same temperature we feel here on the Earth. But a planet's atmosphere plays a hugely important role in the climate of that planet. We can see here we've got sunlight entering the atmosphere, bouncing off the atmosphere, being reflected by clouds. The Earth itself absorbs some of that heat and re-emits it in the infrared, re-emits it as heat. It re-emits it as heat. Sometimes that is then reflected back by our own atmosphere. It escapes into space or is being re-radiated at different wavelengths. So the atmosphere, the clouds, the things in the atmosphere play a huge role in the temperature and the climate of that planet as well. We can see this really beautifully if we look at satellite images of the Earth. What we're seeing on the side here in this kind of green-blue one, that's looking at the reflected solar radiation. So this is looking in the UV and the optical. What light from the sun is being directly reflected back out. On the side here in the blues and the deep reds, that's the emitted radiation. This is the infrared radiation that is given off by our planet. And you can see two different things here. If you look at the reflected light, the hottest, the most amount of reflection is in the white. So the brighter it is, the greener and the whiter it is, the more reflected light. And then in the emitted radiation, the darker it is, the bluer it is, and the whiter it is, that's the emitted radiation is less there. And what you can see is a link between the fact that these areas are reflecting a lot of light, but they're also blocking a lot of radiation from escaping. And those correspond to the cloudy regions around our rainforests over here. So we've got some beautiful clouds across the Amazon. And you can see that those clouds are actually also blocking that heat from escaping our planet. So they're reflecting the starlight, but they're also reflecting that radiation back down towards the ground. So the clouds play a huge role in our atmosphere in heating up our planet and regulating the energy budget of the Earth. But there's a whole host of complications when it comes to planets. They're not simple. It takes a huge amount of things to understand. And one key thing is time. Our planet is not the same planet that it has always been. In fact, we're on about the 4th atmosphere of the Earth. The first atmosphere of the Earth would be considered what we call a lava planet. The entire surface would have been molten. This would have occurred just after the moon forming impact. So a large body about the size of Mars impacted the early Earth. This would have left a big molten rock that would be slowly outgassing nitrogen. That then starts to form the second atmosphere of the Earth, which was dominated by methane and carbon dioxide, these materials that are outgassed from volcanic rocks. You can see water is very much the only constant in our atmosphere. Water is also an outgas from volcanoes and rocks. So we had this early atmosphere dominated by these carbon-based materials. There is then what is known as the Great Oxygenation Event. This is the rise of oxygen in our atmosphere, and it's thought to have been caused by cyanobacteria, bacteria that used carbon dioxide in its photosynthetic reactions to create oxygen. In fact, it is thought that it was so good at doing this, it actually wiped itself out. It used up that carbon dioxide, it produced a load of oxygen, it could not survive in that oxygen-based atmosphere. After that, we see an atmosphere that is very, very similar to what we have today. It's got less carbon dioxide, it's got more oxygen, and essentially the methane is really, really very much gone from that atmosphere. But still, we're not quite at the modern Earth. The modern Earth actually doesn't quite emerge until we see the emergence of the ozone layer. Ozone is 3 oxygen atoms joined together. It is generated in the upper atmosphere, in the stratosphere. This is generated by the impact of UVB and UVC radiation, ultraviolet radiation that is interacting with that oxygen molecules and forming ozone in that process. Ozone can only emerge when you have a high flux of O2 that is below it. That high flux, that high density amount of O2 going up into the atmosphere then gets hit by this solar radiation, it breaks it apart. But in the process of forming ozone, you actually can destroy ozone to form O2 again. So it's a cyclical reaction that is occurring to constantly produce ozone, and that can only happen when we have enough oxygen. So this is now considered the modern Earth's atmosphere. And again, this is the 4th iteration of our planet's atmosphere. So when we're looking at exoplanets and trying to understand them, we also have to understand the time aspect. We might see a planet that looks very much like the ancient Earth, the Archean Earth, as it's called. But through time, 4 billion years, so we might not have the patience for that one, it might end up looking like the Earth. So it's not just a question of, are we looking for the Earth as it is now? Are we looking for things that might look like what the Earth previously did, or what the Earth might look like in the future? And another thing that is really, really important about planets, especially planets like our own, where a relatively slow rotation period, 24 hours, creates these circulation cells in our atmosphere. There are still very barely habitable parts of our own planet. A habitable world, a world within this liquid water zone, does not mean there is water everywhere. It also does not mean that the climate is a nice place to be absolutely everywhere. We have very different biomes across our planet due to the atmospheric circulation. The atmosphere, again, dictates what the surface of that planet is like. This is one of my favorite pictures. I took this in Death Valley. That is one of the hottest places on the planet. It's in North America, in Nevada. There are signs all over Death Valley that say walking after 10 a.m. is not recommended. There is not a single sign which tells you what time to come back. I don't think walking's recommended at any time in Death Valley. It is boiling hot during the day and it is freezing cold at nighttime. So there are still things that are dictated by our atmosphere that really critically show what the climate and the environment of that world is like. So our question is, how can we measure the atmospheres of these distant exoplanets? How can we understand them? What are they made of? What is the relationship between that planet, its environment, and its atmosphere? So I've already mentioned some of the methods that we use to measure these, and I'm going to really focus in on this one method called the transit method. How many people have seen the transit of Venus or Mercury in front of the sun? It is a truly spectacular thing to see. When's the next one? Do you know? Venus is ages away. Oh, that's such a shame. So it's an amazing thing to see. You can look at SDO images, solar images, that you can see Venus and Mercury passing in front of the sun. But we're literally doing this for other stars. So what we're doing is we're looking at these distant stars. They are just a point of light. We are not resolving them or the planets. What we're doing is we're watching these graphs at the bottom. This is what we see. We see the amount of light from the star and we measure it over time. As we measure it over time and that planet passes in front of that star, what we're seeing is the amount of light from that star change. And the amount of light from that star changes because the planet is quite literally blocking out a small amount of that light. By blocking out a small amount of that light, what we're able to do is, if we know the radius of the star, then we can work out the radius of the planet, because the amount of light being blocked is a ratio of the size of the planet to the size of the star. As you can see here, we've got two different sized planets, a giant planet in front of the star and a small planet in front of the star. The amount of light they block is very different. That allows us to make these measurements. However, if this star was much smaller, we would be able to see a much, much larger change in the amount of light for a smaller planet. Because again, it's just the ratio of the sizes. Smaller star, the smaller the planet we can measure for the same change in light. But what about the atmospheres? I've said already the atmospheres really change what we can measure. And one really nice way of showing this is by looking again at our own planet. This is a picture of the moon and the Earth's atmosphere. And one key thing is that the size of a planet will look different at different wavelengths, because the atmosphere interacts with that light. So I'll show you what that looks like. This is a true real color image. It's a kind of composite color image. If we look at the Earth and the moon in 8.6 microns, this is in the infrared, this is what it looks like. And if we look at 9.6 microns, it looks like this. The size of our planet literally appears to change. And that is because at 9.6 microns, there is ozone in the atmosphere that is absorbing that light. If it is absorbing that light, it is blocking more light. If you block more light, you look bigger. Okay? The moon doesn't change, apart from in saturation. The moon doesn't change because it doesn't have an atmosphere. So we can use this measurement to really look across all the different wavelengths and build up a picture of where the light from that star is being blocked as a function of the color, the wavelength of that light. And the beauty of nature is that every atom, every molecule has its own fingerprint on that spectrum. So you might be used to spectroscopy. What we're actually seeing here is the planet radius change. So if something is in the atmosphere blocking that light, the planet will appear bigger. So our absorption spike is up rather than down. So in traditional spectroscopy, you'd see this as a dip as the light is being absorbed. Because we're measuring the size of the planet, and if there's something absorbing in the atmosphere, it appears bigger, we see them as spikes instead. So if we look as a function of wavelength, the apparent size, because of the different things in the atmosphere, will change. And again, the bigger the atmosphere, The bigger, the puffier the atmosphere, the more atmosphere a planet has. Jupiter has a humongous atmosphere compared to the Earth. The bigger the atmosphere, the easier it is to measure that spectrum. What we're seeing here is a selection of different types of planets. Again, we're a say what you see kind of field. Hot Jupiter, Jupiter-sized planet orbiting very close to its star, such that it's about 1,000, 2,000 degrees. Insanely hot, but massive gas giant. Warm Neptune, about 1,000 degrees. We don't know the meaning of the word warm. About 1,000 degrees, but Neptune-sized. Or a temperate Earth, about 300 degrees, rocky planet. The relative size of the blocking light, the relative size of those features, those absorption features in the spectrum, is very, very different. So the bigger the planet, the easier it is for us to make these observations. And one of the beautiful things is, oh, that's an interesting label. It's upside down. We've got planetary mass here versus the radius of the planet. And you can see our solar system in a nice straight line there. They are actually in a relatively straight line. This is a look at a load of the measurements that we've made with the Hubble Space Telescope of the spectrum of different planets of different sizes. So we can see from our giant Jupiters, these are very, very different from Jupiter. They're the same size. They are dominated by hydrogen and helium, but they're orbiting within 5 days of their star. So they're very, very hot. So all of these materials in these atmospheres are gases. So we've measured loads of different things in the atmospheres of these amazing planets. One thing that I spent my PhD doing, and then a significant amount of my time at NASA working at Goddard Space Flight Center, was measuring a whole range of exoplanets with the Hubble Space Telescope to survey the presence of water vapor, water gas in the atmospheres of these planets across that mass spectrum. And what you're seeing on here is the characteristic rise in the light from that planet. So we're blocking it, we're getting a bigger planet here because water vapor is in the atmosphere blocking that light. So in the same way the Earth's atmosphere has water vapor in it that blocks the light in the infrared, it reflects it back to the Earth. These planets have lots and lots of very high temperature water in their atmospheres that we've measured. And about 80% of the worlds that we've measured with the Hubble Space Telescope have this water in them. And that's really important, because water is one of the most abundant molecules in the universe. It is everywhere. It's in ices, it's in gas, it's in liquid, and it is all over the place. We know that it should be mixed throughout these planetary atmospheres. So this is a really great test of us being able to measure what these planetary atmospheres are made of and the different things that are in them by being able to measure these water features. But that's with Hubble. Enter the new paradigm in exoplanet atmosphere observations. And that really comes with the launch of JWST. This is a little kind of spinning GIF of the relative size and type of telescope that Hubble and JWST are. Hubble is a single mirror telescope, whereas JWST is made up of many different segments, about 18 different segments. Hubble is a silver mirror. This means that it works very well for the UV and the optical. It's good at reflecting optical light. JWST is made of beryllium and is gold plated. That gold plating allows it to reflect infrared radiation a lot more, infrared light, the heat, essentially, what we can feel. So these two very different telescopes allow us to look at very different parts of these exoplanet spectrums. But not only that, JWST is 6.5 meters across. It is about 6.25 times the collecting area of the Hubble Space Telescope. So we are able to collect a lot more light from these stars, and therefore a lot more light that passes through the atmospheres to measure what they are made of. And this is in fact on the side here a selfie taken by JWST of itself. It is the first telescope, space telescope to take its own selfie. And I kind of want you to imagine you've got this arm out the front of JWST. That's its secondary mirror. The light's reflecting from those segments at that mirror and going back through the hole in the mirror middle to the tertiary mirror and the instruments at the back. It looks a little bit like a beehive taking a selfie with all of its beautiful hexagon mirrors there. So just because it's an astronomy talk, and I'm sure you guys have got some beautiful images of space, but I want to show you what JWST allowed us to do in just 2 months. This is a picture that I made up of all of the press release images that came from JWST in just the first 2 months of observations, which just showcases the amazing array of science that it can do. That's all well and good. This is what I measure with JWST. We don't take pretty pictures, we take spectra. What this is the light from the star spread out across the detectors by different instruments. So what we're seeing is the footprint of the star's light as it's spread out by different optics in those telescopes. So we've got some fun ones, some hideously curved features. We've got nice straight ones there. And this one, which is like a double ramped feature. So this is the kind of data that we have to deal with to pull out that information that I'm showing you for the spectrum of these planets' atmospheres. So the way that we do that is what I've explained before. We're measuring that spectrum over the course of time. So we get a spectrum, we get a different spectrum every a few minutes or so maybe, and that's spread out across the wavelengths. We can then take different parts of that wavelength space and look at it as a function of time. If we do that for all of the different colors, we'll build up an understanding of the change in the amount of light as a function of that color. And if we do that, we can then translate that to the amount of light that is blocked as a function of wavelength, and we can get the spectrum of that planet's atmosphere from that. So what have we learned? Brand new science has immediately come out of these observations. One of the key things that we have understood is off the bottom of the board, that we've already discovered the presence of photochemistry in the atmospheres of these planets. The starlight is interacting with that planet's atmosphere and it's forming molecules that we wouldn't expect to see there if everything was in equilibrium, if everything kind of just settled down to what it would normally do. The starlight is interacting with those materials and forming different gases. And in this case, this is forming something called SO2, so a sulfur-based material in these planetary atmospheres. One of the most beautiful things that we've been able to do with JWST is get high precision measurements across a whole range of wavelengths that we've never ever seen before for these planetary atmospheres. What you're seeing here is observations that we made within the first month of operations of JWST. This has since come out in a number of press releases, and we had about 6 Nature articles looking at just these, which is exhausting and ridiculous. What you're seeing again is these beautiful absorption features from water in the atmosphere, blocking the light. You've got amazing absorption from CO2 in this planet's atmosphere, which we've never been able to measure before, and SO2 down here. So this is the photochemically generated material. We did this measurement for the same planet 4 different times to confirm how the instruments worked. We were testing this telescope. It's never been tested. The only time you can test a space telescope is once it's in space. So it's a bit of a gamble. So we designed this program to test all of the instruments, understand what they're doing, and all of them overlap in their wavelength range so that we can understand if they're well calibrated against each other. But I don't think this really sells it at all. So I'm going to show you what I think sells it the most and that I still absolutely love watching. This is the spectrum of this planet's atmosphere that was state of the art in 2018. This is a combination of observations from the Hubble Space Telescope in the optical and the near infrared. From this, we were able to measure 3 distinct water absorption features, sodium and potassium in the atmosphere. These two dots out in the infrared are about 3.5 and 4.5 microns, those big error bars. Those are photometric points from the Spitzer Space Telescope. This was the most complete spectrum that we had of any exoplanet ever. This is what 8 observations looks like. This is what 1 observation from JWST looks like. Two important things. How insanely efficient JWST is. Single observation gets us that. It took us 8 to get it before. But also, that's me. That was my work. Wonderful. This gray line was the prediction that I made based on the measurements that I had. Fits pretty well. Quite proud of that. So from our observations with the Hubble Space Telescope and looking at the composition of materials in the optical, we were able to predict that we should see CO2 in abundance in the infrared spectrum. We predicted that we would see it, and we in fact measured it. Not only that, but this measurement was then made by my PhD student, Lily Alderson. So we've got a nice kind of generational link there through academia, which is beautiful to see. We can actually take this and break it down and try and understand what we're seeing in the spectrum. So what I'm showing you here in gray is the data points that I've just shown you. In black is the best fit model to that. So we use chemical networks and radiative transfer models. So we monitor, essentially, we work out what the photon did, how it interacted with different materials in the atmosphere, and we try and understand what would make up that atmosphere. So what I'm showing you in all of the different colors is what would that atmosphere look like if it didn't have this material in it. So if this planet's atmosphere didn't have carbon dioxide in it, we should measure that yellow line. We didn't. We saw this massive peak. So that actually tells us that carbon dioxide is represented by that big peak in the spectrum. Again, you can see the same thing for SO2, which is this pink line here. That bump there represents the SO2 in the atmosphere blocking that light. And we can see some other materials here like CO2 at those very long wavelengths and water at these short wavelengths. So that rise towards the left-hand side, that is evidence again of the water in this planet's atmosphere. So we can use these different chemical models to try and break down and understand what's going on. One of the key things in this diagram is in fact the darkest blue line, which goes all the way down to the bottom. That's what the atmosphere would look like if it didn't have any clouds in it. I already told you clouds are incredibly important for what is happening in a planet's atmosphere. So we're going to just take a quick look at what these clouds are, remembering that this planet is over 1,000 degrees. So clouds in a planetary atmosphere compared to what we would expect to see from the gas actually block and absorb the light in a very characteristic way. If you've got clouds made of very small particles, they'll scatter the light predominantly in the blue. If you've got clouds made of large particles, they will block the light across almost all of the wavelengths. So you can see the impact that they will have on the different parts of the spectrum. So the depth of these features can tell you a little bit about what kinds of sizes the particles of those clouds are made of. But it's not just the sizes that are important here, it's what are they made of. So we can look at our solar system. This is what we call a temperature pressure profile. Temperature along the bottom, pressure, so we're going up in altitude as we go up the diagram. For the Earth in green, we can see that our pressure temperature diagram, we've got our decrease in temperature with altitude until we hit the stratosphere where the ozone layer was absorbing and heating up the atmosphere. And then as we go into space, it gets colder and colder. This is all well and good. Over here, our dashed lines represent different materials that would turn into a liquid or a solid at those temperatures. In our solar system, we've got clouds that are made of methane, ammonia, water. In our exoplanet atmospheres, because they're so close to their star, they're superheated to thousands of degrees. Their temperature pressure profiles start in the thousands and end up in the thousands. Their clouds are in fact made of materials like disodium sulfide, magnesium silicate, sand, rock, the earth, the crust that we stand on, liquid molten iron, and my favorite one, the highest temperature clouds, the corundums. These make up the basis for rubies and sapphires here on the earth. These materials at these temperatures are the things that are forming the clouds in these planetary atmospheres. So we don't have these beautiful water clouds interacting with that light. We've got these clouds made of glass and sand. And that can help us understand more about their energy budget, the importance of the heating of the atmosphere, how much light they reflect, how much light they absorb, and the dynamics of that planetary atmosphere. And we already know from not just our solar system, which would be considered these nice cold planets. This is a representation of Jupiter with its ammonia clouds that we can see. Deep in Jupiter's atmosphere near the core, there will be clouds made of these corundums. If we warm it up, we lose those cold temperature clouds. And if we warm it up further, the higher up in the atmosphere, it's still very, very hot. This is essentially the temperature along here. We get these clouds of these magnesium silicates. And just like atoms and molecules, these materials, these minerals, have their own absorption signatures, because it's all about the relationship between the atoms in those materials and how they move and interact with the light. And this is called a vibrational mode in a mineral. So the rocks on the Earth have an absorption signature that we can measure for these planetary atmospheres. And that measurement is critically in the infrared. So these are the absorption signatures of different materials. And that is far out in the infrared where we haven't been able to measure before. Once again, JWST is here to save the day, because the Hubble Space Telescope has taught us that these clouds exist by the way they scatter the light in the optical. But JWST is going to be able to tell us what those scattering clouds are made of by being able to measure the absorption signatures of those clouds themselves in the infrared. This is a typical absorption signature of glass that would form clouds in the atmosphere, magnesium silicates. So we've kind of taken a little bit of a journey through how we measure these atmospheres and the importance of different things in those atmospheres. And what we're essentially doing is measuring the perpetual sunset. We're looking at the star's light shining through the edges, the limb, the terminator of that planet's atmosphere, as if we were watching the sunset continuously occurring. We know from looking at our own Earth that the environment in which that light passes through changes the nature of your sunset. So we can look in the Lake District. We can see here a nice clear day, a beautiful red sky and sunset with this fading blue. You can look at it in a smoggy day in LA. That smog is a particular size of particle and a particular type of particle which scatters the light incredibly efficiently. So therefore the sky looks more pink and purple, because it's really good at scattering that light. As you head up into space at different altitudes, you again see these colors and the gradients change. So let's go on a little journey to some of these planets and finish up by seeing what the sunset on some of these worlds might look like. To do that, we're going to need our trusty TARDIS, because we can't get there by ourselves. So the first world we're going to take us to, see if these animations work, is what looks like a really alien planet. We're currently sitting in the atmosphere of a planet and looking through that atmosphere at its star. The star looks incredibly green. And this is simply because the atmosphere of this planet contains sodium. Sodium blocks and absorbs orange light. If you remove the orange light from this star's spectrum, we would see through the atmosphere that it would look this kind of green color. We can go to another planet now, and it looks a little bit more like home. quite familiar. It's quite nice. This planet is orbiting a very sun-like star, a little bit more active than our own sun. And we see again the signatures of this red, which means that all of that blue light is being taken away. And that's because the atmosphere of this planet is scattering that light. What we see for this is a really steep scattering profile towards the optical, and that tells us that blue light is being scattered away. However, unlike the Earth, where the blue light scattering is caused by our nitrogen in the atmosphere, this is the scale of the Earth's sunset relative to this planet. We are around a planet that is 22 times closer to its star than we are to the sun. It orbits in 1.8 days. It's about 1,100 Kelvin, and the atmosphere contains clouds made of salt. NaCl, quite literally table salt. Table salt is incredibly reflective. These particles are very, very small in the atmosphere, and they're scattering away all of that light in a very, very similar physical situation to the Earth's atmosphere, but from a very, very different cause. We've measured this planet's atmosphere in reflected light. So we've watched this planet's atmosphere and we've looked at the light reflected from that planet. And just like our Earth's atmosphere, which appears to be blue, this planet also appears to be blue. But as Simon mentioned at the beginning, these aren't tourist destinations. This planet has clouds made of salt traveling at 5,000 miles per hour around the planet. It is worse than standing on a beach in Wales in the winter. We go to my favorite planet now. This is the film noir sunset of WASP 12b. You've got this really, really beautiful kind of fade to that old celluloid green at the bottom there. This planet has a fairly boring spectrum. It's a bit of a flat line. That slope to it suggests that there are scattering by small particles in the atmosphere, but this planet is 2,500 degrees. There is not a single material that should exist in the solid or liquid form at that temperature. Everything should be a gas. Yet we're measuring something that tells us that that's not the case. So what this is telling us is that this planet has very, very poor transport of the heat from the day side to the night side. Because what must be happening as we go around the planet, it must be cooling down to the point where things can form as a solid and liquid. The first thing that will form as a solid and liquid in these planet atmospheres is that corundum. Clouds made of rubies and sapphires in this planet's atmosphere. We are going to be measuring this planet with the James Webb Space Telescope, JWST, and we're going to be trying to observe the absorption signatures of those corundums, that aluminium oxide. So I will finish up there by saying that not only have we seen and we know that our solar system is made of a whole host of incredibly unique worlds, but we're starting to see and understand that in these exoplanets. And yet there are still tons of questions we have, not just about our own solar system, but about what these worlds are like and what that means for understanding the role an atmosphere plays in that planet's environment. If you do want to know more, advertising slide. I have a podcast called Exocast where we talk all about exoplanets. We have different podcasts from discussion sessions where we talk about how we can detect exoplanets, what we can measure, what have we measured, to looking at the very latest in research that's coming out of the field. You can also find Bang 2, 2 exclamation points. This is the 15-year update to the original Bang, which was written in 2005. This was written with Brian May and Chris Lintott. The original book was written by Patrick Moore, and I came in 2020 and we rewrote 9 billion years of the universe's history. I will leave you with this beautiful image of JWST and point out that within this amazing array, you can see the science that we do, which is turning beautiful points of light into squiggles. But I think it's some of the most pretty things that we're learning about the universe. So thank you.
Thank you, Hannah. Okay, so let's open up to the floor. What amazing questions have you got? What bits did you go, wow? Which bits did you go, oh, I didn't understand that? And what's questions? Yeah.
I had a question. It was to do with something you said earlier about the presence of oxygen on Earth being due to life on Earth.
So,
Cyanobacteria.
yeah.
If you discovered oxygen in an exoplanet, would it indicate life on that planet?
No, unfortunately not. So oxygen is not only generated by life. Now, the amount of oxygen we have is indicative of life, but you can produce oxygen in the amounts that we could measure without the requirement of their life producing it. So one of the key things in trying to understand how we can detect and understand if something is habitable or inhabited, which I think is the key question people actually want, is looking at an imbalance in the materials. So one of the things that exists in our atmosphere is the presence of both CO2 and methane. Those two things shouldn't exist at the same time. So what we'd be looking for is an imbalance in materials that can only exist at the same time in certain amounts. So there's too much methane that's produced by life on Earth, mostly cows farting, actually, because we actually see patches of it over different parts of the atmosphere. So what we would be looking for is an imbalance in materials and amounts of those materials which doesn't match up with what could naturally be occurring through other means. But that is an entire field of study of people trying to understand what are those? How can we, what we call abiotically, create materials and therefore allow us to rule out the fact that what we're actually measuring is a dormant planet? It's a tough one. We'll get there.
How did you feel? Because when they did the reveal photos of JWST,
Yeah.
the first science, everyone went, wow, that's pretty. And look at all those amazing galaxies. And then the graphs came up, which the graphs effectively you're showing us.
Yeah.
And I went, it's a graph. But what it was telling you was so much more.
So much more.
Yeah.
And, you know, I was at the National Astronomy meeting from the Royal Astronomical Society on the day they released them. We were doing a big panel talking through them. You know, we were sitting in the room watching people see these images for the first time. And, you know, some of them are on here. This one in the middle there is the galaxy lensing. The one right at the top with the beautiful blue background is my favorite one from that. Absolutely gorgeous contrast here. This is the Carina Nebula. It's a star-forming region. The group of galaxies, interacting galaxies down here as well. You know, all of those images, like you said, were absolutely mind-blowing. And they're really, really nice to look at. But what we got immediately was like pure science. We were able to see that and understand, okay, well, we've measured water in that atmosphere, but not only that, it didn't look the way that we expected it to. There was a huge amount of clouds in that atmosphere blocking the light in a very specific way. So we didn't know that, we didn't expect that. So that first spectrum that we saw allowed us to get an insight into how we could use JWST to really understand more about these environments. And I thought that was one of the most exciting things to see. And I think it's the same for everybody that saw them. So I have a friend who was talking really excited about the galaxies and the lensing galaxies and looking at the deep universe. And he was like, oh, this just opens up so many more questions. And I think all of us felt like that. It's just like, oh, we've got some work to do because there's so much in there that we don't understand.
Online, have we got some questions from those at home? You can unmute yourself and ask your questions. So feel free.
Yeah, I've got a question, Simon.
Tony, yeah.
It was a very interesting talk, Hannah. Thank you. Towards the end of your talk, you mentioned that one of the exoplanets you were observing in reflected light. Given that you're observing transits, I was just wondering how you managed to do that. That must be very little light you're observing there.
Yeah, so actually the reflected light is happening as the planet passes behind the star from our point of view. So as it passes behind the star, just before it does so, we're seeing the full day side of that planet reflecting that light. Or in fact, if we're looking with JWST, the light being emitted directly by that planet. So we can measure on the opposite of the transit is the secondary eclipse, where the planet is blocked entirely by that star. So we can use that to really understand what the day side of that planet is like. And if you look with the Hubble Space Telescope, you can look in the UV and the optical to see that reflected component. And then if you look with JWST, we'll be able to see that thermal component from the planet itself. So combining that information together is going to allow us to really understand the nature of that image that I showed you of the Earth, the reflected light, where it is and how it's structured, and then the thermal component as well.
Yeah. Okay, thank you. So you can actually observe.
So very hard.
Yeah, you can actually observe reflected light with the Hubble Space Telescope as well, can you?
So far for 2 planets.
So it's restricted, it's difficult.
Yeah, that was one of them. That's one of the brightest stars with a giant planet around it that we can make that measurement of. That is a 5.5 magnitude V magnitude star. There aren't too many stars that bright with giant planets around them where we can make that measurement.
Okay, so it has to be a big star with a big planet.
Yeah, it's all about signal to noise. It's all about how much light we can collect. And that is really a limiting factor.
Okay, that's great. Thank you.
Yeah.
Is there a correlation between how far away the suns that you're monitoring is to how many planets that they have, exoplanets that they have around it? In other words, are we seeing more exoplanets the further back you look because you've had more time to develop?
So we're looking within our own galaxy. So we're not actually looking really too far back in time in that respect. They're very much, I think the furthest ones that we're looking at are maybe a couple of 100,000 light years away. So in that time period, the Earth's been the modern Earth the entire time. So we aren't able to really look at the atmospheres of anything that's far enough away for us to be able to look at that kind of thing. But one thing that we can look at is the age of the star. So the age of the star is going to be really key as to how evolved that planet is. And what we've done is we've looked at stars that are around, planets that are around stars that are just being born, like just forming. These are still within their disk. There's still gas around them, or there's still rock around them. So understanding their atmospheres, and then we can look at some of the systems I've shown you today. Those are what we call evolved, in that they are middle-aged. They're like the sun. They're about 4 billion years old. They're settled. They're very much, happy where they are. So they've been like that for a long time. So they're in this kind of state where we think they've been like that for a while. But what we do in astronomy, as you know, is we take snapshots. So the key thing and the beauty of exoplanets is we can take snapshots across a whole load of different stars, a whole load of different ages of stars, lots of different sizes of planets. We can get those snapshots and we can build that up into a full picture in history. We have one snapshot of our solar system. If we can look at these kinds of systems, really young, really old, we've seen some around evolved stars. We've seen some around white dwarfs, dead stars. So looking at these snapshots of thousands of exoplanets, we can piece together that story of planet formation and understand and place our solar system within that as well. Yeah.
So is that the ultimate goal of your work? Is it to make a major contribution to that story?
Yeah, I'm all about big picture. I want to understand, what is the role of the environment on an atmosphere? How does that atmosphere really dictate what that world is like? And how can we translate to understanding the nature of our own solar system? we have the opportunity to kind of look out at these thousands of worlds, whereas, you know, we can't study Uranus and Neptune in the same way we can study these exoplanets. One of the planets I'm looking at right now is the same size and mass as Uranus, but it orbits so close to its star that all the materials in its atmosphere are in the gas phase. I can measure that. I can measure the spectrum of a gas. We have no idea what the constituents of Uranus's atmosphere are and how much there is, because it's in solids, it's in clouds, it's dropped down deep in the atmosphere. It's all locked up in materials that are very hard to measure. So if we can take these planets, we can stick them by a fire, we can heat them up, we can measure them, we can actually understand more about our solar system planets by looking thousands of light years away than we can by going to them in some ways. Yeah. And we've got hundreds of them to play with.
What's the impact, though, of the bias on your research? The fact that there are a whole sort of family of planets out there that we haven't got a technique to observe, and the data just isn't there in creating that big story.
Yeah, so there's a couple of things that you need to piece together for that story. One is called demographics, which is looking at populations and distributions of orbits of planets. There's a new space telescope called the Roman Space Telescope, which will launch in the 2030s. That's going to be surveying a large part of our galaxy to look for the population of planets that are like our solar system in terms of their orbital distance and their mass. That will give us a picture of how common that is, because it will break a lot of that observational bias that I showed you in that diagram. But we can't look at their atmospheres. We have no idea what those planets will be like. We'll be able to measure their mass and their orbital distance, and that's it. So that's one thing that kind of fills that gap. The work that I do with JWST and Hubble is really diving into these atmospheres and understanding the impact that environment will have on those planetary atmospheres. And I like to look across all of the mass ranges. I love the giant Jupiters all the way down to these rocky planets to try and understand if there's a relationship there. So that's like another piece of the puzzle. And then another piece of the puzzle is then looking at the ages of these stars, understanding what the stars are made of, looking at planets that are using a different technique than transiting ones, so on really, really wide orbits and really giant planets. So to understand our own solar system, our place in it, requires a huge range of techniques and different things. But rather than having a single data point of our solar system, we can use this huge number of test tubes, these little planetary test tubes that we've got, to really look back and see where does that one data point fit in the collection. And I think that's one thing that we've been missing. When we first discovered exoplanets in the 90s, it rewrote all of the books about how we thought planets formed. One of the key updates in Bang is actually the story of our solar system's formation. Discovering giant planets really close to their stars told us that planets move over time. They don't form in their orbit and then stay there forever. These giant planets cannot form that close to the star. There isn't enough material around the star at that location for it to even be able to exist. So it formed further out and moved in. So that history of the fact that it had to move told us, okay, well, if planets can move, could our planets have moved? And that developed a whole host of different theories and understanding of our own solar system. So we have learned more about ourselves in the last 20 years looking at these and the discovery of these exoplanets than we had in hundreds of years just looking at our own solar system, because there's so many things that one data point can't tell you. So I think I know there's a ton of stuff that we don't yet know what to look for, and we're going to find, and we're going to learn so much from it.
And then write Bang 3.
And then Bang will need an update at some point. I don't know how quickly it will need an update. You'll notice the first chapter of Bang is very similar to the first chapter of the first Bang. But I do think we're going to need an update again.
Is it wrong yet?
No, not yet.
So in the last 3 years or so?
Not yet.
Yeah.
Not yet. I was careful about that. I left a little redundancy in the system.
Hannah, could I ask another question? When you find a planet and you can't detect an atmosphere, do you think that's because there never was one, or do you think perhaps it's been blown away by the stellar wind, or the temperature's too high for it and it's boiled away?
Yeah,
Or,
so
so do you think planets generally form with atmospheres?
yeah, so we have to use that kind of information about the temperature, the distance, the age to understand what might have happened. But we believe that all planets are born with what is called a primordial atmosphere, which will consist of hydrogen from the solar nebula. The Earth was born with a primordial atmosphere before it got hit by Theia, which created the moon. That primordial atmosphere of the Earth was a hydrogen envelope, so hydrogen gas from the solar nebula. A majority of that, not all of it, got blown off by that explosion. But we do think that all planets start with that. Now, how long it can hold on to that is due to something called Jeans escape. So the velocity of material, so everything's moving all the time. If you give it lots more energy, it will move faster. The lighter that material is, the easier it is for it to reach the velocity needed to escape the gravity of that planet. The Earth's escape velocity is 11 meters per second squared. That meters per second, not squared. That escape velocity for hydrogen, because hydrogen is so light, means that you really don't have to give it that much energy for it to just dissipate into space. So we can see that with our own atmosphere, that we've lost a majority of our hydrogen. And in fact, we've lost a majority of our helium as well, because that is also light enough to reach that escape velocity. So we can look, and we can, from the mass of the planet, we know what its escape velocity is going to be. So we can use the understanding of that Jeans escape to work out whether it lost that primordial atmosphere or not. And you can also work out how heavy an atmosphere would need to be for it to be able to hold on to it by its own gravity. And then you can look at the temperatures and the relationships there. So there's a couple of things that we piece together to try and build a hypothesis for what that atmosphere might be like. And then if we can't measure that, that tells us either that, you know, that hypothesis is wrong, or that it's actually something else that we're not able to measure with our signal. So we're still in the process for these very small planets of beating down our signal to noise. The noise is too high. Our uncertainties, our error bars are too big. We can't tell anything other than the fact we're not seeing a primordial hydrogen atmosphere. But we'll get there.
Yeah, okay, that's great, thanks.
Okay. All right. Well, again, hands together. Say thank you to Hannah for coming along and giving us a great talk. Don't forget to get your copies of Bang 2 and also listen to Exocast. And thank you very much.
Thank you.
Thanks, everyone.